In this chapter, we're going to be talking about using integration to solve problems. And specifically, we're going to be talking about double or iterated integrals. We're going to start by looking at iterated or double integrals over rectangular regions. So if I want to integrate a surface in space, so I have the surface z equals f. Let me show, there we go, z equals f of xy, that's what I've drawn in this picture, the surface in space. I could integrate it over a region in the xy plane. The region R is technically what we call a projection, or the shadow that that surface is making over the xy plane. We can set this problem up as a double integral by integrating the function over that region R. Technically, what we're doing, if we want to think back to those Riemann sums, is we're actually adding up the heights of this surface times these little, I guess we'll call them delta A's, these little kind of rectangular regions. And so we're basically, you could think of it as adding up, I guess, volumes of these kind of three-dimensional solids that cover this region. So this is our kind of natural extension to integrating in 2 dimensions. In 3 dimensions, we can integrate a surface over a region in the 2-dimensional plane. Now, hopefully this will start to make more sense as we do examples, and so I just want to dive right into examples. I'm not going to talk much about the Riemann sum definition. You can read about that more if you're interested. I really want to focus on, in this particular section, how do we actually set up and compute these double integrals? So let's start by just doing an example of a double integral and talk about how do we actually do this computation. So the problem says, evaluate the double integral xy minus 3xy to the third dA over the region R. So we have this surface, that's what's inside my integral. The function that we're integrating is our surface, and we're integrating it over this region where x varies from 0 to 2 and y goes from 1 to 2. So the first thing I'm going to do is I'm going to actually sketch that region that we're integrating over. And so that's what I've done on, I guess it's on the left side of the screen in pink. So the region that we're considering, the x's go from 0 to 2, and the y's go from 1 to 2. So we're talking about integrating over this rectangular region. And we can set this problem up in 2 ways. We can integrate the function with respect to y first. And notice that if you put the dy first, then the bounds on this inside integral are going to be your y values, which go from 1 to 2. So we can integrate with respect to y first, and the y's vary from 1 to 2. And then after that, we'll integrate with respect to x, and the x's go from 0 to 2. We can switch the order of the integration. We could integrate with respect to x first. Again, the x's go from 0 to 2. Or we can integrate with respect to y, and the y's go from 1 to 2. So I think the thing I really want to point out here is that you can think of this as kind of a nested set of integrals. And so when we do the computation, there's an inside integral we're going to do first. And so the bounds of integration on the inside integral symbol go with, in this case, the dy. So the idea is we're going to do our inside integral first, and then after that, we'll deal with our outside integral. And so these bounds, in this case, the 0 and the 2, go with the dx. All right, so this is the problem we're trying to solve. And so I'll integrate with respect to y first. And so if I want to integrate with respect to y first, I'm just going to focus on this inside integral. So I've circled it in yellow. So that's the part I'm going to look at, and I've just copied that integral on the bottom of the screen. Okay, so we are going to integrate xy minus 3xy to the third. The dy means with respect to y. So to do this integration, I think of it as really similar to our thought process when we did our partial derivatives. We're integrating with respect to y. So we treat y as the variable, and everything else is constants. So this first term, we've got this xy. We treat the x like a constant, so it stays there. And then the antiderivative of y is y squared over 2. So the first term becomes xy squared over 2. Same process with my second term. Minus 3x stays there, that's like our constant. And then the y to the third becomes a y to the 4 over 4. Okay, so I find my antiderivative, and then I'm going to plug my bounds of integration, the 1 and the 2, in. So again, we integrated with respect to y, so those bounds of integration are y values, and they are going to get plugged into the y's. So I'm going to take my antiderivative, I'm going to plug 2 in for the y's, then I'll plug 1 in for the y's, and then finally I'll subtract those. So I think, unless I made an arithmetic mistake, I don't think I did, I ended up doing lots of computations. I got negative 39/4 x. So the thing to notice here is when we integrated with respect to y, and it's a definite integral, so we integrated with respect to y, and then we plugged the y values in, I think one of the things to notice is that there aren't any y's in our final answer, but our answer might have x's in it, might have the other variable. Okay, so what we've done right now is we just figured out that this integral that I circled in yellow can be evaluated to negative 39/4 x. And so now what we're going to do is we are going to compute the integral from 0 to 2 with respect to x of that answer, negative 39/4 x. So we replace that inside integral, what I have underlined in yellow, with the negative 39/4 x. And now we just integrate with respect to x. So that becomes negative 39/4 times x squared over 2. And then I'm going to plug my bounds of integration in. I plug in the 2, I plug in the 0, and I subtract them. And I got negative 39 halves. All right, and so that's my final answer for this double integral. Here's another one. Let's integrate square root of x over y minus y. We're going to integrate it with respect to y and with respect to x. The y's go from 2 to 4, and the x's go from 1 to 9. So I'm going to start with that inside integral. So I'm going to be integrating with respect to y first. So y is like the variable, everything else is the constant. So that first term, I'm going to think of it as a square root of x times 1 over y. The square root of x, I treat that like a constant, so I've got square root of x, and then the 1 over y becomes a natural log of y. And then the second term, the minus y, we integrate that, we get y squared over 2. And then I'm going to plug in those bounds, and the bounds I'm talking about is the 2 and the 4. So I'll plug, I'm plugging them in for y, because we just integrated with respect to y. So that gives me square root of x times ln 4 minus 4 squared over 2. And then square root of x minus ln 2 minus 2 squared over 2. So I got ln 4 times root x minus 8 minus ln 2 times root x plus 2. I might as well group these terms with root x together. I could write that as ln 4 minus ln 2 times root x. And then minus 8 plus 2 is minus 6. And now I'm going to go ahead and take this solution that I just got. That was my inside integral. I'm going to plug that in. And finally, I'm going to integrate with respect to x. And then use those outer bounds of integration, the 1 and the 9. So let's see, ln 4 minus ln 2 is my constant. Square root of x is the same as x to the 1/2. So I get x to the 3/2 over 3/2. And then the minus 6 becomes a minus 6x. And then I'm going to plug my bounds of integration in. I did some simplification here. Let's see. Dividing by a fraction, you can flip and multiply. So I wrote that first term as a 2/3 ln 4 minus ln 2 x to the 3/2. And then I did one more thing just to simplify. That ln 4 minus ln 2 can be simplified using those properties of logs. That's the same thing as natural log of 4 divided by 2. So I just went ahead and simplified that to natural log of 2. So ln 4 minus ln 2 actually simplifies down to ln 2. So I did that just so I had a little bit less kind of writing to do. Okay, so now I've got, let's see, 2/3 ln 2, and then I plugged in the 9, so 9 to the 3/2 minus 6 times 9. So that's right here, and then I'm going to plug in the 1 and subtract them. So lots of arithmetic. Hopefully I didn't make any mistakes. Let's see. Well, there's my scratch work. Cross that out. I didn't have a calculator when I was making this. So let's see. We did 2/3 ln 2, 9 to the 3/2, minus 6 times 9. This is what I had before. Minus 2/3 ln 2, 1 to the 3/2, minus 6 times 1. 9 to the 3/2 should be 27. 27 times 2/3 is 18. So I got 18 ln 2 minus 54 minus 2/3 ln 2 plus 6. And then I did some combining of like terms, and I got, let's see, 18 minus 2/3 was, oh, that was my scratch work, 17 1/3. So 52/3 ln 2. And then minus 54 plus 6 is minus 48. You can double check my work on a calculator if you want, but there is my final answer for this double or iterated integral. So the idea is you do one integral at a time. You start with the inside and then work your way out. When you're doing your inside integral, it's okay for your answer to end up having variables in it. But then when you do your outside integral, the variables should disappear. You should end up with something that's just a number. All right, so why are we finding double integrals? What do double integrals tell us? Well, double integrals are going to give us information about both area, volume, and give us information about average value. So first of all, if you want to use a double integral to compute area of a region, you can actually just integrate the constant 1. So if you just integrate the number 1 over that region, you'll end up getting the area of that region. We can extend this if you have a surface that has positive z values, if you have a surface that's above the xy plane, something like this, and you integrate it over some region, you'll end up getting the volume of that region. And we'll definitely do more examples of that later on. So if you just integrate 1, you get the area of the region. If you integrate a surface, you're actually going to end up getting a volume. All right, and then on the bottom half of the screen, I have a formula for average value. So the average value for a function of two variables over a region R is 1 divided by the area of that region times that integral. This is similar to average value of a function of one variable. It was 1 over the length of an interval times the integral, something like that. Okay, but let's focus on examples. So let's see if we can find the average value of the function f of xy equals x cubed plus 2y over the region 1, 3 by 2, 4. Okay, so first of all, this notation being used for R is something that your textbook does. It lists an interval of the x's first and then the interval for the y's. So that region is saying basically the x's go from 1 to 3 and the y's go from 2 to 4. So that's first of all what that notation is telling us. So we're talking about this rectangular region. Again, the x's go from 1 to 3, the y's go from 2 to 4. And so our average value function or formula, if we want to find the average value of this function, we're going to take 1 divided by the area of that rectangle times the integral of the function over that area. So I guess first of all, what is the area of the region we're looking at? It's a rectangle. I can see in my picture it's got a length and a width of 2. So the area of that rectangle would be 4. 2 times 2 is 4. So plugging that into my formula, my average value is going to be 1/4 times my integral. And I'm going to integrate with respect to y first, and the y values go from 2 to 4. So I put 2 to 4 on my inside integral, and then I'll do the x's, and those go from 1 to 3. So let's start with our inside integral from 2 to 4, integrating with respect to y. So antiderivative of x cubed is just going to be x cubed times y. Remember, we're treating that x cubed like a constant, so constant times y, x cubed times y. And then the 2y turns into 2y squared over 2, or just y squared. And I'm going to plug those bounds of integration in. So let's see, I plugged in the 4, and we're working in terms of y, so plug them in for the y's. So plug in the 4 for the y's, and then I plug in the 2 for the y's, and then I have to do some simplifying. I ended up getting 2x to the third plus 12 when I was done simplifying. So then I'm going to take that answer, the 2x cubed plus 12, and that I'm going to integrate with respect to x, and my bounds are 1 to 3. 2x to the third becomes 2x to the fourth over 4, and then plus 12x. And then I plug in the 3, plug in the 1, and subtract those values. I did a bunch of arithmetic. Ended up getting 64. So average value would be 1/4 times 64, or 16. So it would be the average value of this function over that rectangular region. Now, in this particular video, we really have just focused on setting up these integrals over rectangular regions. And when you're working with a rectangular region, whether you do the x's or the y's first, it doesn't matter. You just want to make sure you're looking at the appropriate bounds. But where we're going next, just looking ahead, is we're going to talk about how do we deal with these integrals if we have a region that's not rectangular. So in this section, when you're figuring out your regions, we're always going to be looking at rectangular regions. And then we'll save looking at more general regions for the next section. All right, that was my last example. Please get in touch if you have any questions about this video.